Artificial Intelligence Doctor. www.abcpharma.net/English user question. What are the specific molecular mechanisms through which acetic acid, the primary component of vinegar, modulates hepatic glucose production and improves peripheral insulin sensitivity? GPT-4o answer. Acetic acid, the primary component of vinegar, modulates hepatic glucose production and improves peripheral insulin sensitivity through several specific molecular mechanisms. Here's an overview of these mechanisms. 1. Inhibition of carbohydrate digestion and absorption. Alpha amylase and alpha glucosidase inhibition. Acetic acid inhibits the activity of enzymes like alpha amylase and alpha glucosidase, which are responsible for breaking down carbohydrates into glucose in the digestive tract. This slows down the rate of glucose absorption, leading to a reduced postprandial, after-meal, blood glucose spike. 2. Suppression of hepatic gluconeogenesis. AMP-activated protein kinase, AMPK, activation. Acetic acid activates AMPK in the liver. AMPK is an energy sensor that, when activated, inhibits key enzymes involved in gluconeogenesis, the process by which the liver produces glucose. This leads to a decrease in hepatic glucose output. Reduction of acetyl-CoA carboxylase, ACC, activity. By activating AMPK, acetic acid also reduces the activity of ACC, an enzyme involved in fatty acid synthesis. This shift promotes fat oxidation over glucose production, thereby reducing gluconeogenesis. 3. Improvement of peripheral insulin sensitivity. Enhanced GLUT4 translocation. In skeletal muscle cells, acetic acid promotes the translocation of glucose transporter type 4, GLUT4, to the cell membrane. GLUT4 is responsible for glucose uptake from the bloodstream into muscle cells. Improved GLUT4 translocation increases glucose uptake and utilization, enhancing insulin sensitivity. Inhibition of lipolysis. Acetic acid inhibits the breakdown of fats into free fatty acids, lipolysis, in adipose tissue. High levels of free fatty acids can interfere with insulin signaling pathways. By reducing lipolysis, acetic acid helps improve insulin signaling and glucose uptake in peripheral tissues. 4. Reduction of inflammatory markers. Decreased pro-inflammatory cytokines. Chronic inflammation is linked to insulin resistance. Acetic acid has been shown to reduce the levels of pro-inflammatory cytokines such as TNF-alpha and IL-6. Lowering inflammation improves insulin sensitivity. 5. Modulation of gut microbiota. Alteration of gut microbiome. Acetic acid can influence the composition of the gut microbiota, promoting the growth of beneficial bacteria. These bacteria produce short-chain fatty acids, SCFAs, which have been associated with improved insulin sensitivity and reduced systemic inflammation. 6. Direct effects on pancreatic beta cells. Enhanced insulin secretion. Some studies suggest that acetic acid may have a direct stimulatory effect on pancreatic beta cells, enhancing insulin secretion in response to glucose. This helps in better glucose regulation. Conclusion: acetic acid exerts its beneficial effects on blood glucose regulation through a combination of mechanisms involving the inhibition of carbohydrate digestion, suppression of hepatic glucose production, improvement of peripheral insulin sensitivity, reduction of inflammation, modulation of gut microbiota, and potentially direct effects on insulin secretion. These multifaceted actions make it a promising dietary adjunct for managing blood sugar levels, particularly in individuals with insulin resistance or type 2 diabetes.